Welcome back, everyone. So let's talk about trees. Uh, so the first representation, and this is the most widely used representation um, of any sorted data structure, is a binary search tree. Now, what happens in here in this type of binary search tree is that uh, if we have an element at the top, let's say 8, the left side or the left node of this element is less than 8, and the right node of this element is greater than 8. And so this constraint is followed throughout the tree for every node. And the first thing that you will notice is that in a tree, there is this exponential relationship between the number of nodes at any depth d, which means that if I talk about, let's say, the root or the top node where the depth is 0 or the height is 0, I know that there is only one node there. At d is equal to 1, we have a couple of nodes. At d is equal to 2, we have 4 nodes, 2 to the raised power 2, although in this case we don't have a left node of this node 10, but uh, if it's a complete and balanced binary tree, then at the second level we have 4 nodes. And likewise, if we go to d is equal to 3, we know that we'll have 8 nodes, or 2 to the raised power 3 number of nodes at d is equal to 3. Okay, so there is this exponential, or let's say logarithmic, relationship between d and n. Now this is useful in the sense that every operation that we do in trees, including searching, including insertion, including or including deletion, actually depends upon directly upon d, not on n. What that means is that, imagine that if we have to look for a number, let's say 5 in this case, what you'll do is that you'll simply check that whether or not 5 is, let's say, greater than or less than 8. If it's less than 8, which obviously it is, then we go to the left. Then we check whether 5 is greater than or less than 3. If it since it's greater than 3, then we come over here, and then we check that whether 5 is less than or greater than 6. Since it is less than 6, we move to the left. And so therefore, at maximum, we need to have 3 hops to find, let's say, any element, which means is that the searching for any particular element is dependent upon the depth or height of the tree, not on the actual number of nodes that we have directly. Obviously, d depends upon n, but every operation will have direct dependency on this depth of or height of tree, which is presented here by d. Okay. And likewise, if we talk about insertion, the approach is very similar. Just keep inserting, or keep traversing until you find a balanced root node, and then insert item over there. In terms of traversal, what we have is the so-called in-order traversal, where we basically alternate between recursive calls of this in-order traversal to each node. Okay, and so this is like this class is customized by yourself, which means that I've, let's say, written this class myself. But if you are using Java, then you don't need to do this donkey work yourself. We have a TreeMap object that is supposed to do exactly what you have done using your customized node class in here. Okay. And so what you can do is that instead of writing this whole class, and instead of writing in each of these methods, you can simply use TreeMaps to do exactly that. So let's say we have a tree map where the uh, where actually we will have keys which are integers, and then some names as value value pair for that particular key. Okay. So these keys are basically, let's say, these numbers that are to be maintained in a sorted tree. So what you can do is basically simply put key value pairs in this tree map, and that tree map will automatically insert your value at correct depth within that tree. Okay, so you don't need to write this whole class of node and then override or let's say define these custom insertion and searching and in order traversal methods yourself. Everything is done by the stream app itself. And so if you put you decide to insert your keys at any order, if you just put out, or let's say if you just traverse this hash map, you'll see that it will automatically put those key value pairs by ascending order of your keys. Okay. uh, and another thing to notice is that we said that in some video we actually discussed that the maps themselves are not iterable, right? So we saw that maps themselves are not iterable, which in this case is true. But if you just think the keys as a set, then the set itself is iterable. Okay. And what this means is that if I if I just query the entry set, which will basically give me the whole key value pair, you can iterate over keys, you can iterate over values, or you can also iterate over both items themselves. Okay. But you cannot simply say that this entry is a variable of type tree map, so I'm not basically directly iterating this key tree map. I'm actually iterating on the entry set of this tree map, which is a collection of key value pairs. Okay. So the tree map itself isn't iterable, but the key value entry set is iterable. Now this is obviously so far so good, but what if we don't have these integer as our sortable keys? What if I have some different class that I've written myself? Okay, so this brings me to our previous video where we discussed, let's say if I have an employee class of a name and an attribute and a salary attribute of a particular employee, how am I going to, let's say, sort that array list of employees which we saw earlier? The alternative was to use a tree map to actually store employees in a particular order rather than sorting a predefined list of employees um, post priori. So what we can simply say that let's say if we have some comparator interface that implements this comparison of two employees, I can simply define my tree map by passing an instance of this comparator interface while I'm defining my tree map. Okay. So this tree map, obviously what it does is that this tree map actually thinks of an employee as a key, and then some garbage integer that I've just created to put a value for that employee. So the employee itself acts as a key, the employee object, and then some integer that represents this employee. Okay. And now I can simply say that just take this tree map and put, let's say, create a custom employee and put this employee as a key and then some integer value as its value. And so if you keep inserting these different types of employees, and as if you keep inserting these different types of employees as keys and then corresponding integer values, the tree map, since this tree map automatically sorts your key value players by ascending order of the keys. If you remember, we saw that uh, you know these associative containers, actually it's a collection of unique keys which is sorted by keys themselves. So Java, when it defines tree set or a tree map, it automatically assumes that you are going to sort by your keys. Okay, now the what you can do is, you can define this sorting method yourself, but this sorting method will be applicable only on your keys, not on your values, right? So what we have done over here is that we are going to insert our employees as keys, and then automatically, if you have defined a comparator interface and pass this as an argument, the sorting will be defined by this compare method that you have passed to an object of this my comparator type. Okay, um, and so this will be done internally. What you need to do is basically just define an interface that implements your comparison and pass that interface, while defining your tree map, and then start using your employee class as keys. And then if you see, if you just print out your employee tree map, it will automatically sort your employees based upon your custom comparator interface, which in this case is salary. Okay, so the lowest salary will be printed first and the highest salary will be printed in the last. Okay, so in the next video we are going to see different traversal strategies in generic trees.